Okay, it's been a while since I made a video for machine design class, but here's one for rolling bearings. I'm going to try to be a little bit more efficient, be a little bit quicker, try to get some stuff done in class to make that flipped class thing a reality. Okay, I want to point out right away that I'm using some figures from Shigley's 10th edition. I hope that you will buy Shigley. I hope this is a good advertisement for buying Shigley. This shouldn't replace getting the text. We're talking about rolling bearings, which include ball bearings and roller bearings, and which include things like needle bearings, and a general arrangement of a shaft with bearings. We'll often see some form of way of keeping them in place with an end cap. Sometimes there'll be like a Belleville spring or a series of Belleville springs, which are look like washers that are concave. That as you apply the end cap onto there, kind of keep a positive axial load. And ball bearings have these balls that are running inside these inner and outer races. And what's important to recognize is that any kind of bearing uses a little thin film of lubricant. This whole topic falls under the category of tribology, something I'm not an expert in, but I want to point out that it's a big field. And could be there's lots of more information. This is just skimming the surfaces. All right, there's lots of different types of bearings. The ones that I think are important to us: the deep groove, angular contact. We might say self-aligning. We'll see. We'll hand out some in class or look around at them to look more closely. Both the angular contact and the deep groove can handle some amount of axial loading as well as radial loading. Radial loading being the primary thing that we care about. On the angular contact, they can handle more. This doesn't show it, but there's usually a little bit of gaps between or a difference in curvature between the race and the ball, just slightly enough that this outer can shift when an inner can shift, and that causes that the load can be carried at an angle. There's also other types of roller bearings. I mentioned the needle or tapered roller, spherical bearings, lots of different types of bearings. Fundamental engineering that's going beneath the surface, so to speak, because that's sort of a pun, is this contact stress, which we spoke on a little bit. I pointed out with if we took a little pencil and I pressed it against the desk, right here, if we looked really closely, we would say that area right there at the interface would be infinitesimally small, which would make the stress skyrocket, infinitely large. We know that can't be, so there's got to be something else going on. And that's going to be local deformation. And it could be very local stresses, but it's mostly going to be deformation that's going to take up. And some of the things that are going to happen is that the area is going to increase. It's not going to be a point area. That deflection when it comes to a spear and a flat plate right here, it's going to end up with a circular area because of the deflection. You could also have a sphere against a sphere, also a circle, or we might have a cylinder on a cylinder, which will come up with a rectangular area of contact. This is going to be discussed again when we talk about gears, spur gears, in the engagement between them, very much like two cylinders rolling against each other. But for our situation, we have most closely for a ball bearing having a sphere inside this curved raceway. One of the important aspects to think about, and one of the reasons why we bring this up, is how the stress is distributed in Hertzian, which is the name given. Mr. Hertz got his name famous here, not only for frequency but also for this type of stress. where there's a compressive stress that gets distributed. And my understanding, or what I've heard before, was that there's the very peak stress that will happen because of this. If you were to take like maybe the von Mises of this condition, you would find that it would be just underneath the surface. And the result of that, when there's highly loaded, is that a little chunk can get spit out because of where that high stress is located. And the result of that is a pit, which is one of the common things in the failing of contact stressed pieces. Another explanation also of the failure in ball bearings was given from this fine book right here, Applications in Mechanical Engineering, where we have a little crack or just some disturbance in the microstructure there allows for some lubricant to go beneath and then expel a chunk of the surface. Of course, we're talking very small, little tiny micro things, but the result of that could be something that's called a spall, which is this area of disturbance. So you may have run across or experienced some damaged maybe ball bearings or something along those lines, where you've seen the pits in the spalls, and you can kind of appreciate how they get initiated. And okay, this is just a summary of the things I've said already. That comes down to what the fundamental thing we want to do in bearings and ball bearings is to establish the load-life relationship. And the issue that we have at hand is we have our desired conditions that we want to have for our design, how we want to use the bearing, but we're given only a small amount of information from the manufacturer. They've come up with some numbers that they provide you, and they're not going to be identical to how you're going to use the bearing. So you want to make this apples to apples comparison. So we want to convert their numbers into our numbers, or our numbers into their numbers, so we can make a real comparison. And the things we need to change, to change it, is the longevity, how long we want our bearings to last, and how reliable we want it to be, and the kind of load that we're going to have versus what was given in the catalog. The two catalog numbers that are given most often are the static load rating and the dynamic load rating. And we'll see what this C10, that's the most important one, we'll see what that 10 means in a minute. But these are often called the basic load rating. Here's what's given in the text in Shigley as an example of representative catalog data, and we could see that with the C10 and the C0. This is for the deep groove, and this is for the angular contact right here. Everything is given in metric units, by the way, in the text, and it will be in these problems. Here's an excerpt from the NSK catalog. They're a big ball bearing manufacturer, or roller bearing manufacturer as well. Just to give as a comparison or contrast to what was given in Shigley. You can see that it's presented a little differently. The big thing that you need to do as a real engineer, as a working engineer, is to try to figure out what the manufacturer, for whatever particular thing that you're using, their conventions, and how they intend for you to use them. All right, so bearing life, this is the essence of trying to do these problems. We have a big capital L life, which means revolutions, and cursive life, which means hours. And we could see down below how they're related to each other. It's just be cursive L times the RPM times 60, so that we can get into the number of hours of a life for the bearing, how long it will live. Now, how long will it live? Well, it'll be dependent on the load that's applied to it and what we consider life. And in this case, life is going to be considered when 10% of the bearings fail. That's going to be 90% reliability. All right. And for 90% reliability, and one common limit for the life, and that's the big L, is going to be 1 million revolutions. What happens if you plot a bunch of different data points of bearings failing at a particular, and you vary the different load, you'd find that it ends up being a relatively straight line on a log-log scale. So this is log F and this is log life, log force, log load, and log life. And a curve fit between them has been found to generally follow this FL raised to the 1 over A, where A is 3 for ball bearings and 10 over 3 for roller bearings. Well, we're mostly going to deal with ball bearings. So with this relationship here, them equaling a constant, we can make this apples to apples comparison. So you can see that this is the fundamental thing that we're doing. We're trying to convert our condition, our desired load, and our desired life into a catalog rated load, which is often called the C10, right? So you can see that we can go and we can use this, our desired load, our desired life. There's the rated life, which is often 1 million, but we have to look it up to see what the manufacturer is basing their C10 on. And if we want greater than 90% reliability, we're going to have to shift making a compensation for that. And we use that with this Weibull distribution. What we have right here, we're showing the relationship of a curve. And these different parameters right here give you the shape of this curve and the skewness, and you use these shape parameters so that now we can come up with a new life or a new adjusted life, where this XD is going to be this ratio of life to life. We'll see this in a second as we do a problem. All right, and to get these parameters, you might have to go to the manufacturer. In our case, we have an example that's it's not located on page 608, somewhere else. But anyway, we have these parameters that we could plug in there for a particular manufacturer. In this case, manufacturer 2 is the one that's some company, they're not giving us the name of it, has a rated life of 1 million cycles. And other things we need to do are to be able to combine radial and axial loads, or thrust loads. And the way in which we do that is to apply a table and this equation right here. And a brief explanation of it is we have this curve that for this non-dimensional parameters right here of equivalent to radial and axial to radial. We find that at a certain point E, below a certain point E of this FA to FR, the axial does no longer matters. If you'll see this parameter yi is going to go to 0 below E, right? And so the only thing that's going to end up matter below that is going to be the radial, and we'll see that this value xi goes to 1 at that point below E. Right, so, and then just a quick comment on the V right here. That's something that's a rotation factor. It's going to be 1 if the outer ring is stationary. That means, by contrast, it's 1.2 if the outer ring is rotating. That would happen if the shaft was stationary and then you had something that was attached to the bearing, some type of a wheel or whatever, and it was rotating. So the outer race is rotating as opposed to the inner race is rotating, which would be like something like a pump shaft where the housing was attached to the outer race. Okay. So here's the graph, or here's the table that you use with that equation above. You could see that if this ratio right here is less than E, then Y goes to 0, right? And X is 1. So that means that with the YI, which is Y1, if that's the case, that you're only the radial load is the only thing that's going to matter. You're not going to need to use any of the axial load to be able to adjust and come up with an equivalent load. If it's greater than E, now we have this distribution where we have, okay, we use like 56% of the radial load, and then the axial load will go and have an influence. And which parameter do you use? You base it on what the axial load divided by the static load. That's the C0 you can get from the catalog, right? And then noting that if it's below 0.014, you just go ahead and use the values of 0.014. Because we're using this table, when we have to combine these, we're going to have to do an iteration of this table, which could be a little challenging. So that'll be something we're going to look at. One of the things I want to discuss just quickly is preloading. I mentioned with the Belleville springs on the end caps, that tends to put a force and shift and give a positive force between the bearing, even when there's no load being applied to the thing. It's already preloaded. That is a way to increase the fatigue life. One thing I think that's a good way to associate is that it removes any gaps that you might have, some clearances. Like if you can imagine, if there was no load going on right here axially, this ball could move all over the place because of the little tiny gaps. By having a preload on there, it establishes where the points of contact are going to be. And like I said, it does also increases the fatigue life generally. You're not always going to have the same amount of load on in an application. It might change over time, and you're going to have to do something to accommodate for that, where we come up with the idea of what damage is, and we say the damage is going to be the area that you would form for a particular load and the amount of time that it's going to apply. We could call that damage. And then we say if we have a different load for a different amount of time, we could say that area is damage, and we could take that damage and we could add them up and divide by the total amount of time. We could raise it to this 1 over A, which because there's a curve going on in here. And we could come up with this equivalent amount of load. And so like we could do all the things that we had previously done for adding the radial and axial together, and for each of these, and then the amount of time that were put together, and we could come up with this total equivalent load. So that's a complicated problem. We could also have load factors that we could put on top of this this load rating, because we're going to try to look at the catalog load rating, which is really made for a complete radial constant load that's at a constant and non-changing load onto the thing, right? So if there's precision gearing, you could say, okay, it's close to being equal to what the catalog was, but we might want to put a little bit more on there. If it's commercial gearing, we might want to increase what our considered load is, so we can compare it to this nice, perfect, constant load that's in the catalog. All right, so summary. Here's the equation that we use if we have 90% reliability and it's all radial load, and we could even use this. We could substitute FD if we do combine the radial and axial, or we combine and we get in a total equivalent with the varied loading. We could put that in for FD, and we could find this catalog rating. Just noting that conversely, we might also want to estimate how long will our bearing survive, and we could then solve for the LD in there if we know what the catalog rating is, what our external load is going to be, and what the manufacturer's considered life is going to be for 10%. If we will need that equivalent radial load, we're going to use this equation right here combined with that table 11.1. And then we've also discussed the equivalent radial load. And then if we want greater than 90% reliability, we're going to have to come up with this dimensionless life measure right here, where we take this ratio right here, and We put them in there for the XD, and then we also establish this Weibull distribution life. And then once again, I want to emphasize that that little a is this order of load life agreement. It's 3 for ball bearings and 3/10 for roller bearings. Okay, so here's the problem. So we have this 02 series single row deep groove ball bearing with an inner race rotation, and it is selected from table 11.2, which is considered manufacturer 2, to support a radial load of 10 kilonewtons and axial load of 5 kilonewtons. The desired life of the bearing is 12,000 hours, operating at 300 RPM with a reliability of 95%. Okay, so we've entered in all the various junk that we can. And from the problem statement, we can look these things up right here. And we can assume that the load factor is going to be 1. So right off the bat, we could say that our life, our desired life, is going to be 60 times our number of hours, right, times our RPM. So that's simply going to be 60 times 12,000 times 300. So we're going to end up with 2.16 e to the 8 revolutions, which is obviously going to be more than the 1 million. If we looked up in the table, we find that manufacturer 2 is based on the 1 million revolutions, 1 million cycles. Okay, so we know we're going to, because the reliability is 95, we're going to have to find that dimensionless life parameter XD, which is LD divided by L10, which is the manufacturer, is going to be that 1 million. So we end up finding that it's 2.16 e to the 8 divided by 10 to the 6, which is really e to the 6, so we get 216. Could have done that in our heads. And one of the first things we're going to have to do is find the axial and radial relationship. If we take the V, which we know V is going to be equal to 1, I guess I had it up there, and FA over FR, we're going to find that's going to be 5 divided by 10, right? So we end up with 0.5 is going to be that FA over VFR. All right. So first what we're going to do is we need to do a preliminary evaluation. So we're going to use the this equation right here. Okay, that's the load factor, and I'm just writing the whole thing, not skipping any steps. X0 plus right here x0 times 1 minus RD raised to the 1 over B raised to the 1 over A. So in our application, that's 1. We have a 10 as going to be our radial load to begin with. 216 is that parameter. We looked this up right here, that XO is 0.02 from the table for the Weibull distribution. That theta is 4.459, and then we could subtract out the 0.02. Quite often in some of the examples, they'll just do that one step. That'll get you a little confused. Sometimes you might see a different number, and it's because they played fast and loose and didn't bother to tell you that they skipped step. That's messed me up before in the past. Okay, so raising that to the 1/3, because that's A is equal to 3, we get a 70.79. Once this is the catalog rating under which we would base everything if it was completely radial load, which we've done. But this is our first pass guess because we needed that C10. We'll see that we use that C10 and look up in a catalog what bearing would we have, because we need CO and we don't have that yet. We need to find a bearing. So if we go to table 11.2, we can find that for the 85 millimeter bearing has a C10 of 83.9 0.2 kilonewtons, which seems that it would work. Its C0 is 53.0, okay, kilonewtons. So we use that, this is our first guess, and we go to table 11.1, and with that we have an FA over CO that we use, and we have this 5, that's our axial load, divided by 53. And we find 0.09434. Now that's not a value in our table, table 11.1. So we need to interpolate to find E. So we find E by interpolation. And I often will set up an Excel spreadsheet to find this. And this is how I do an interpolation. I don't remember when I learned how to do this, but it was a long time ago. And I do it the same way every time. So here you go. Desired value, and then value above. All right. And so I have for, I think this is going to be my FACO, and above, the next value up is a 0.084. Our value is 0.09434, and desired above is 0.11. For the E, we get a 0.28, right? And a 0.3 is our value above. Now, quite often I'll go X right here, and I'll just do the ratio, and I'll say, I'll start out here, and I'll go there to there, there to there, there to there, there to there, set a ratio, and then solve for X. So I would have something along the lines of 0.11 minus 0.09434 divided by 0.11 minus 0.084 equal to 0.3 minus X, just being sure that I go in the same pattern, 0.3 minus 0.28, right? And I solve for X, and I would find X being E right here, that I get a 0.2880. Okay, now I need to, now we know that E is going to be, okay, we need to find FA over FR, which we calculated previously, right? Which is, it was 0.5. Because 0.5 is greater than this value of E, we're going to have to, we're going to find that X2 was equal to 0.56 from the table, and Y2 we have to find from interpolation. That's lovely, isn't it? So we do the same thing here, and I'll just draw the table. I won't go through the process right here. All right. So we go 0.084. Here's the parameter that we're using, that FA over CO, and that's 0.09434 and 0.11, and the Y2 that we need is 1.55 and 1.45, and if we find this right here, we find that Y2 is going to be equal to 1.510. And that, this is of course why I go ahead and I use an Excel spreadsheet, because who wants to keep doing that over and over again? So now I want to find the equivalent, so I use this equation, Y2FA, and I find out 0.56, V is 1, FR is 10, plus 1.510 times 5, okay, and I end up with an equivalent load of 13.15 kilonewtons, right? Now, then what I end up having to do is calculate my C10 again. and this is 13.15. I've just entered in, and all this other stuff, 216 divided by the 0.02 plus the 4.459 minus 0.02, 1 minus 0.95, that's the 95%, 1 over 1.483, right? And I'll extend that over to 1/3, and I find that it's 93.09 kilonewtons, which is more than that previous C10 that I used right here, right? This is the one that I used, that I picked as my first guess because it looked like it was going to be good enough. But sure enough, I can't use the 85 millimeter bearing. I need to go up to another level up, maybe even 2 levels up. So you can see this is part of the iteration process. So because now I need to pick another bearing. So if I go to the table and I pick out, this is table 11.2. If I pick another bearing, I could pick the 90 millimeter bearing, which has a C10 of 95.6 kilonewtons and a C0 of 62.0 kilonewtons. And if I do that, I find an FA over CO of 5 over 62, which should give me 0.08065. Right? And if I do that and I interpolate, I get an E of 0.2775. My 0.5 is still greater than that, so I use the X2. I find an X2 of 0.56, and I interpolate again and get Y2 out of that table. I get 1.570, and then I apply it again and get my equivalent is equal to an X2 V FR plus Y2 FA, and you can plug the numbers in yourself. We get 13.45 kilonewtons, and our C10 then 1 times 13.45. We could have saved ourselves some time, by the way, of calculating what this inside this was going to be, and I didn't need to necessarily write it down every time, but why not? I have it written out that way. It's repetition is a good thing in teaching, maybe not in engineering. 1 over 1.483, right, raised to the 1/3, and that ends up coming up to 95.22 kilonewtons, which is below our actual catalog that we chose. So we say that this is good, good enough. Maybe we want to go to the 95 millimeter bearing, maybe. But we don't want to oversize everything just based on just based on being conservative, because it costs more money to get a bigger bearing. All right, so that's the end of the video. Hopefully this wasn't too long, and we can do some work in class based on what you've seen here. Thank you.